next time. All right, so the chain rule is really kind of something that we use if we're dealing with taking a derivative of a composition of functions, primarily is the idea. So the idea would be like if you had something like, you're used to writing this like f composed of g of x, okay? A lot of times we write that as f of g of x. So if we're doing a derivative of a composition of functions, there's a certain way that you go about doing this. Now we're going to try to be fairly technical about this. It turns out when you actually start getting used to doing the chain rule, and you use it all the time for differentiation, you don't really think of it too much as a composition of functions, but that's the way to start, giving you the idea how that goes. So the idea would be the chain rule kind of goes like this. Say, for instance, you have a function that's a composition like this. Like if you had something like f of g of x, kind of like this. And if we let u be g of x, okay, if we just kind of substitute that like that, then we could think of this function of f of u like that. So what happens on this is when you do a derivative of a composition of functions like this, you end up doing two things. You do the derivative of y with respect to the variable u, and then you multiply that by the derivative of u with respect to x. This probably won't make much sense until I go through and start showing specific examples to show you how that goes, because we're going to look at two versions of this. We're going to look at this Leibniz notational system and more this type of situation. So if you're doing a derivative of a composition of functions like this, then what you do in this notational system is you take the derivative of the whole thing, and then you multiply by the derivative of what's inside, which would be that second function g of x. Again, this stuff right here won't make any sense to you until we look at examples, okay? I mean, that's just the technical talk of the math. Once you do examples, and you can go back and read that definition, and trust me, it'll make a lot better sense to you then, okay? So what we're going to do on this is we're going to go down to this example one. I'm actually going to show you three ways to do this, and ultimately this third method is what you're going to get so used to doing that once you get the hang of it, you'll do it over and over again, so you'll think of it this way. So let's go ahead first of all on this, and at this stage, the only way that you know how to do this problem is just multiply it out. Just FOIL it and then differentiate. And let's go ahead and do it this way, but you're never going to really have to do it this way anymore after this then. So when we FOIL this out, you're going to get 9x to the second plus 12x plus 12x plus 16. And you can do this in your head. So that's 9x squared plus 24x plus 16. Okay, so if I want you to find the derivative, okay, now you can just do this, hopefully just second nature. What's the derivative? 18x plus 24. Okay, so that's the derivative. Now what we're going to do is we're going to look at the chain rule, and we're going to look at these two different versions of this. So what I want you to do is let's write down what we're differentiating. And you want to think of this as a composition of functions. Okay, you want to write down kind of like this. There's this inside part of what's being squared. There's actually two things going on this. Okay, the first thing that you can do on this is you can think of this as two functions. You can think of this as y equals u to the second. It's something being squared. Then you can think of u as 3x plus 4. This is a composition of functions. This thing that I highlighted, think of that as u, and then think of that whole thing squared like that, okay? So you can write this as a composition of functions. So what we're going to do, according to the chain rule, when we do dy dx, when we do the derivative of this function, we do two things. We do the derivative of y with respect to u, which we're going to do that in just a minute, and then you're going to multiply that by the derivative of u with respect to x. Okay, like that. Okay, and it's actually a very easy thing to do. What students oftentimes struggle with is breaking this down into a composition of two functions. You got to look at it the right way. Okay? Now, this part's going to be easy for you. It really is. What is the derivative of u squared? 2u. So write it down. Okay? And that takes care of that part. Now you're going to do the derivative of u with respect to x. So what's the derivative of 3x plus 4? 3. Write it down. So what you get is you get 6u. Okay? However, we don't want to write the answer that way. You want to plug back in. You want to do a substitution like this. U is 3x plus 4, so plug it in. Then that will be your answer. And then we'll multiply it out. You'll see it'll give the same answer anyway. So this is 6 times 3x plus 4. So notice when you multiply that out, that's 18x plus 24 anyway. Okay, does that make any sense? Kinda, at least. Usually takes a little time for students to grasp this chain rule in that way. The second way is always seems easier for students to grasp a little bit better. But the idea is you can think of this as a composition of two functions. It's something squared. So what you do is the derivative of u squared, then you do the derivative of the inside part, then you multiply them together. That's how a chain rule works. Okay? And we'll do a little bit of repetition and it'll help you kind of get the hang of this. Now, here's the way that you're going to learn to do this most of the time. Okay, so this is method 3. This is what you're going to use more often than you use this first method, that method I just showed you. Okay, so here's what you do. Just think of you're differentiating something to the second power. So when you differentiate something to the second power, what are you used to doing?
Product rule.
Yeah, just bringing down that power rule. So you do 2 times that something, then you subtract the exponent. But the chain rule says you have to multiply by the derivative of what's inside. And what's inside is that thing right there. Okay, so this is what you're going to end up doing then, is you're going to multiply by the derivative of 3x plus 4. Okay, and once you get the hang of this, this is the way you're going to start thinking of this. So what is this? This is 2 times 3x plus 4 to the first. You don't change that. You just write it down. And then what's the derivative of 3x plus 4? That's 3. So notice what you end up getting on this is when you, and that shouldn't be a 2, that should be a 1. So you end up getting 6 times 3x plus 4. So you get the same answer. You get 18x plus 24. So what I'm doing in this case is I'm just thinking, okay, I just pretend like that 3x plus 4 is just like an x. So what you do is you bring down the 2, leave that alone, subtract from the exponent, but then you got to remember to multiply the derivative of the inside part. That's what the chain rule is. Does that make any sense? Okay. Now at the side, let me just do one more. You don't have to write this down, but let's say, for instance, you had 2x plus 1 to the 1,000th power. The chain rule comes in real handy. You wouldn't want to multiply that out 1,000 times. When you do the derivative, here's what you do. You bring down the 1,000, leave that alone, subtract from the exponent, and then you multiply by the derivative of what's inside. That's done. Isn't that easy? Okay, that's what the chain rule tells you to do. And it applies to all kinds of functions, any type of a function that can be written as a composition of functions, of two functions, okay, like that. Okay, let's move on.
Where did you get the 2 outside of parentheses?
This thing right here?
Yeah.
Okay, because I'm multiplying by the derivative of what's inside. Because when you do the chain rule, this is pretty standard. Bring that down, leave that alone, subtract 1 from the exponent. That's what you're used to doing. But since this is something other than just x, since that's another function, then you multiply by its derivative. You multiply by the derivative of what's inside. Try to think of it that way. Okay? Okay. Let's go to this next example here and do this with 2 methods. So the first thing is we're going to do this with a composition of functions. I like to show this both ways. There's a lot of students who like method 1 better. Ultimately, you get to where method 2 is what you do all the time, but sometimes as a beginner, you like maybe to do it more this way. All right, so what we want to do is you want to think of this as a composition of functions. And when you look at this particular example, the way I look at this is there's 2 things going on. The first thing is something is being raised to the 10th power. So that would be like when you write your composition of functions, you can write this like this. You can just call that whole thing right there u. U is just the variable we use all the time, okay? So you can think of this as two functions. You can think of this as y equals 2 u to the 10th, like that. And then you can think of u as being what's inside and being raised to the 10th power. So I'm going to write that down as 3x to the third minus 4x to the second plus 6x minus 1, like that. Okay, so that's your composition of functions. What you're really doing is you're doing something to the 10th power, but then you're plugging that in like that. Okay, now according to the chain rule goes like this. If you want to find dy dx, the first thing that you do is you do dy du. Okay, so you do this derivative that I'm circling there. You're doing the derivative of y with respect to the variable u. Then you multiply that by du dx. What that means is you're taking the function u and you're doing the derivative with respect to the variables x's in that expression. So it's actually easy to do. All right, so what is the derivative of 2u to the 10th? 20u to the 9th, right? Okay, that's done. What is the derivative of this stuff right here? 9x squared minus 8x plus 6x. Oh, 6, not 6x. 6. I know that. Okay. All right. Okay. So now what we need to do is you just need to replace the u with what it's equal to. Okay. You want x to be your variable, so that thing plugs in to that c. Then you're ready to write your answer. So the final answer would be 20 times 3x to the third minus 4x to the second plus 6x minus 1 to the 9th times 9x squared minus 8x plus 6, like that. That is the final answer to that derivative, like that. So if you want to use that approach, that's how you would do that. Okay, does that make any sense? Tell me. Not bad, okay.
And you don't want to multiply that out.
You can, yeah. You don't really have to multiply that out. You're thinking about taking the 20 times that. You can, you don't have to. It's in a factored form, which is fine. Okay, so that's fine. Okay, does that look any good? Okay, here's the other way. This is the way I'm going to do this most of the time. We'll kind of get away from doing it this way more. So if you want to do the second way, you're going to do it just kind of totally in your head. Okay, first of all, you have a constant. Okay, you can just write that constant down if you want to, and this is the way I'm going to do it. You can, anytime you have a constant times a function, just write it down. You don't need to use a product rule, you just write it down. Now, just focus on this part of the problem right here. Here's how you do it. Just think of something to the 10th power. So what do? You bring the 10 down. You leave what's in the parentheses exactly as it is. Don't touch it at all. You subtract 1 from the exponent, so that's 9. And then what do? You do the derivative of what's inside. Okay, now you can write this in one step if you want to. So what's the derivative of what's inside? 9x to the second minus 8x plus 6. Okay, well, that's it. That's the calculus. Now you could clean it up a little bit. You know, you can multiply the 10 times 20 if you want to. So you would have 20 times 3x to the third minus 4x squared plus 6x minus 1 to the 9th times this. Okay? And you can multiply some of this out if you want to, or you can just leave it alone. It's the same answer, isn't it? So which way would you rather do? I'm curious. Second way or first way? Okay, that's what most people think. Not always. So there are some students who do understand method 1 better for whatever reason. But ultimately, you get to a point where you just start looking at it that second way. Okay? All right, does that look okay? All right, chain rule. Everything in this section is going to have something to do with chain rule. So let's go to this next problem here. All right, so we got a square root. So the first thing that you really want to do on this is you want to write this as 10x to the second plus 4x, all to the 1/2 power. I mean, go back to when we learned how to just do something simple like, if we were doing the derivative of the square root of x, what did we learn to do? We just said, write it like that, and then when you did that derivative, you did 1/2 x to the 1/2 minus 1, right? That's it. What's different about this problem, though, is it's not just an x under the radical, it's a whole another function. So it's a composition of functions. So what you're going to do is, to use this first method, is you're going to express this as two functions, okay? And then we're going to use the chain rule looking at it that way. So this part right here, that's the u. So you end up with y equals u to the 1/2 power when you do that substitution. And then you have u is equal to 10x to the second plus 4x like that. You're expressing that as a composition of functions, okay? So now when you do this derivative, dy over dx, you're going to do two things. You're going to do this derivative first. You're going to do the derivative of y with respect to u. Then you're going to do this derivative. So you're doing the derivative of u with respect to x, okay? Now, one thing I want to point out on this is only to help you to remember this rule. If you kind of look at those du's as sort of canceling out, don't you just see a dy dx in there? So you can kind of think of it that way, and it sort of helps you remember the order that you do that in. So what I want to do next here is, let's just do these two derivatives then, okay? So how do you do the derivative of u to the 1/2? That's power rule, right? So you do 1/2 u to the 1/2 minus 1, so I'm going to write that like that. Okay, then you multiply by the derivative of u, which is easy to do in your head, so that is 20x plus 4, like that. Okay, so we've done the two derivatives of the two functions. Clean it up a little bit. This is 1/2 u to the negative 1/2 times 20x plus 4 like that. And then what I need to do at the very end, what's the last thing I need to do in this problem? Yeah, I got to resubstitute. This thing right here that I'm highlighting goes in there. Then we write the answer. Now, and we can, I'm not going to simplify this one very much. Some of these problems I'm going to simplify, some of them I'm not going to. I want to just not spend all the time on simplifying. So we're going to say 1/2 times, and then this gets plugged in now, 10x squared plus 4x to the negative 1/2 power times 20x plus 4 like that. Okay, now there's several things you could do to simplify that. I'm not going to take the time to do that, but think about some things you could do. You could make the negative exponent positive. You could change it back into a square root form, things like that. I'm not as concerned on this example as the simplification as I am the derivative. Okay, so does that make sense? Okay. Okay. Now let's do this second method. So the second method, you want to rewrite the problem as 10x to the second plus 4x all to the 1/2 power. Okay, and you look at this problem kind of like this. I have something to the 1/2 power. If I have something to the 1/2 power, what I'm doing is I'm kind of thinking power rule. But you have to use a chain rule because you have a function that's being raised to that 1/2 power. So when you do dy over dx, using the chain rule, here's what you do. You bring down the 1/2. You write the function in the parentheses as it is. You don't change it. I always see students want to do a derivative there. No. What you do is you subtract the 1 from that. Then you multiply by the derivative of what's inside. Okay, so I'm going to have you just kind of write it out like that. That's how the chain rule goes. One more step and we're pretty well done. So this is 1/2 10x to the second plus 4x to the negative 1/2 power times, and then this derivative here is going to be 20x squared plus 4. Same answer. What did I miss there?
You wrote it the right way, you just said it the wrong way.
Oh, I said 20x, but I didn't write it. Okay. Is that better? Okay, all right. Okay, so that's the idea. How's that look? Okay? Chain rule. Everything in this section has to do with chain rule. It can get kind of tricky too. So we're kind of looking at a specific type of problem right now. And you got to learn how to know when to use a chain rule too as part of what you're learning. Okay, so let's see. Let me give you a little time to do 2 problems using both methods. Yes?
You're saying that most of the time we're going to use that second method?
Yep, that's what you get used to doing. I hardly ever, when I do a derivative, even think of it the first way. They're really the same thing. They really are the same thing. But it's kind of good. There are reasons why it's good to learn that first method. There will be times when it's better to use that. But mostly, if I'm just having you do a derivative, you just do the second way. If that's what you catch on to, that's what you do. That's quicker. So I'll let you guys go ahead and work on it a little bit. One thing I wanted to kind of start you with is, let's get these functions kind of built together. And you guys don't need to simplify. I don't want you to take the time to simplify on these things. I just want the derivative done. We'll do some simplifying on some other examples as we're doing these then. That up, if you're not simplifying, these problems shouldn't take you too long to do. So this first example, I find that when you do the first method, sometimes students don't set them up right. So you're just thinking of something to the 100th power. So y is u to the 100th, where u is what's inside the 2x minus 13. All right, so when you do this, dy du would be 100 u to the 99th, okay? Then when you do the derivative of u with respect to x, you should have got 2. So you end up getting 200 u to the 99th, and then what do you got to do? You got to plug back in for u, okay, because you want your answer to have x's in it. So you would have 200 times 2x minus 13 to the 99th power. That's it, okay? If you do this the second way, without having to break it up into 2 functions, you just go like this. When you do dy over dx, you're doing something to the 100th power, so that comes down. The 2x minus 13 is left alone. You subtract 1 from the exponent, then what do? You multiply by the derivative of what's inside. Okay, that's the idea. Okay, so you get the same answer. This would be 100 times 2x minus 13 to the 99th. This derivative here is 2. And you can multiply the 100 and 200 to kind of clean that up, and then you're done. Okay, so that shouldn't be too bad. Okay, does that make sense? Everybody okay? Okay. All right, now this second one here, I've got it set up as we're doing something to the, this is supposed to be a 1/3 power right here. A cube root's a 1/3 power, so you're doing something to the 1/3. That something is u, or 3x to the third minus 4x squared. Okay, so we're all ready to set this up. So if you do the derivative of u to the 1/3, it would be 1/3 u to the 1/3 minus 1. Then if you do the derivative of u with respect to x, that's going to be 9x to the second minus 8x like that. Okay, and then this is going to give 1/3 u to the negative 2/3 times 9x squared minus 8x. And then what's the last thing I do? Plug in, replace the u with what it's equal to. And I'm not going to simplify it. You can leave the exponent as negative on this one if you want to. So we're going to then have an answer to the problem. Okay, so the final answer, we'll just write this as 1/3 times 3x to the third minus 4x squared to the negative 2/3 times 9x squared minus 8x, like that. Okay, does that look reasonable? I think that should be a 1/3. I kind of copied that wrong like that. Okay, is that good?
You should be the negative.
What's that?
Isn't the negative 1/3 minus 2?
I think I'm okay. 1/3 u to the negative 2/3, so I'm okay. You just don't need, I'm not having you simplify on this one. Okay, if you do it the second way, just go like this. Just bring the 1/3 down. Leave the inside part totally alone. Don't touch it. I always see students do that. They want to do the derivative now. You wait till later. Then that will become negative 2/3. You can do this in your head if you want to. The derivative of the inside part is 9x squared minus 8x. Problem done. Okay? All right. Any questions? Okay? Now, we can kind of look at the chain rule in lots of different ways. I mean, every function can, as long as you got compositions of any two functions, that's how that goes. Okay, now if you look at this one, now these have got some trigonometric functions and stuff in it. They got some exponentials and so forth. So as I'm doing these, I want to remind you of a few basic rules. When we do example 1 on the next page, if you have f of x equals e to the x, well, what's f prime of x? Have you got that one down by now? Good. Okay, it's e to the x. That's the simplest one to learn, right? Okay, well, this is not the derivative of e to the x. It's e to the something. Okay, so what we're going to do on this is, if you want to do this using the first method, and I'm going to get away from the first method after a couple more of these, you would have to write this like this. You would have to write this as y equals e to the u, with u being 10x to the second minus 5x. Okay, what you're trying to do with this is e to the u. You know how to do that derivative. So what's different is that exponent. So if you did this first method, if we did dy over dx, we would do dy over du times du over dx. That's how you would do this, okay? So, let's start this out. What is the derivative of e to the u? E to the u. Okay, we're going to multiply by the derivative of 10x squared minus 5x. What's that? 20x minus 5. Okay, like that. Okay, now what you need to do is u is this part right here, so that plugs back in like that. So you would have, as an answer to this problem, you would have e to the 10x squared minus 5x times 20x minus 5. That's your derivative right there. Okay, so what you're doing is the derivative of e to the u times the derivative of u. Okay, if you want to do this using this second method, which is what you're going to get mostly comfortable with, here's what you do. You look at it as, I'm taking the derivative of e to the something. So think of it as it's itself times the derivative of the exponent. That's a real helpful way to think of differentiating an e to a power using the chain rule. So what do? You just leave this alone. E to the 10x squared minus 5x. Okay? Don't do anything with it. Don't touch it. Now multiply by the derivative of what's inside, or not what's inside, what the exponent is. So that's 20x minus 5x. Okay? So that's how you would handle an exponential like that, is you would just itself times the derivative of exponent. Does that make sense? Okay. What's that? Oh, 5. Okay, not 5x. Sorry. Okay, like that. All right? All right. Now remember, I taught you this rule. I don't know why the textbook even taught you this rule, because it's unnecessary. They said that when you do the derivative of e to the kx, it was ke to the kx. That comes from the chain rule. Okay, if you're doing the derivative of e to the kx, here's what you do. It's itself times the derivative of the exponent, which would be k, right? Okay, that rule was not even necessary to teach. Textbooks do that a lot because they're trying to simplify some things before you get to the chain rule. Okay, all right, now let's look at a cosine. Now this time, I'm going to look at this one. I'm going to do one more with both methods, and then from then I'm going to transition for the rest of them pretty well to just the second method. Okay, so what you have to know on this one is you have to remember this. Okay, and you guys are learning your rules, so you may not have them all down yet. Do you guys remember what the derivative of just a basic old cosine is? Negative sine t. Okay, you want to get those down, the trig functions down, start studying those and getting the derivatives of the 6 trig functions down. So really what we do on this is not the derivative of cosine, it's the derivative of cosine of something else. So you would say u equals 5t to the third, and then you would say the function we're going to do is f of u is equal to cosine of u, like that. Those are the two functions you're going to do. So if you're going to do the chain rule in this Leibniz notation, you would say, you would really be doing dy dt to start with because of that variable. So you're going to do the derivative of y with respect to u, and then multiply that by the derivative of u with respect to t. If you get this backwards, a lot of times students don't get this backwards, you can kind of think of the du's kind of going away. Okay, so you end up with what you're going for. All right, so let's do this then. So what is the derivative of just this part right here, the cosine u? What's the derivative of cosine u? Negative sine u. Okay. Now, what's the derivative of 5t to the third?
15t squared.
15t squared. Okay. So that means that when you resubstitute back in the u, you would get a derivative negative sine 5t to the third times 15t to the second, like that. That's your derivative. Okay. So this second way, the way you do this the second way is you just do this. If you're doing the derivative of a cosine of something, the rule is it's the negative sign of that something. Okay, but then you got to multiply by the derivative of whatever that angle is. So now you do the derivative of 5t to the third. So you would get as an answer negative sine 5t to the third times 15t squared. Now, if you're doing this problem, I would prefer that you write your answer like this. Put things in front of trig functions because it looks better. Probably the best way to write this answer is negative 15 t to the second sine 5t to the third, like that. So again, what you're doing when you're doing a derivative of a trig function, it's whatever that derivative is times the derivative of that inside part. That's the idea. Okay? All right, does that look okay? All right, so we're kind of extending the basic derivative rules to a more general thing. And that's what the chain rule basically allows you to do then. Okay? All right, from now on, I'm just doing the second method. So here's what you do. Okay, always think of the basic thing. Okay, if you're doing a derivative of the sine of x, what is that? Okay, so what we're doing is we're doing now the derivative of the sine of something else. Okay, so when you do the chain rule on this, you're going to do the derivative of that something else times the derivative of that inside part. Okay, that's what the chain rule tells you to do. So when we do this derivative, step one is the derivative of a sine is a cosine of whatever that function is. Okay, then what are you going to do? You're going to multiply by the derivative of that inside part. Okay, well, let's do this. So what we're going to have is cosine of e to the 2x. All right, now technically you would do a chain rule again on this. So what you would have is the derivative of this is what? E to the 2x times the derivative of the exponent. Now, technically, that's what you're doing, is you're doing a chain rule again, because all you know is the derivative of e to the x is e to the x. Well, this is not the derivative of e to the x. This is e to something else, say. Okay, so what you do is when you're doing the derivative of 2x, that's going to be 2. So your final answer would be, okay, you have the cosine of e to the 2x times, and then this derivative, the derivative of e to the 2x is e to the 2x times 2. So that means the final answer, the best way to write this is 2e to the 2x times the cosine of e to the 2x, like that. Okay, that can be a little tricky on that. So what you're doing is the derivative of the sine is the cosine. Then you do the derivative of the inside part, which ends up being 2e to the 2x, like that. Does that make sense? Okay. All right. Okay. All right, let's do this one. Okay, what you need to remember on this is two things. You have to know two things to do this derivative. First of all, what is the derivative of e to the x? Okay. This one's an easy to remember. You guys will, once you start doing your homework, you'll get these. What's the derivative of the tangent? Secant squared x. Okay. You can look them up until you get them down. So those are the two things you have to know to do this problem. So what you're doing is you're doing a e to some power. So really, when you do this derivative, it's going to be, I like to try to get students to think of, when you do the derivative of an exponential, it's itself times the derivative of the exponent. That's kind of a chain rule version of that. So what we do, f prime of z, we're going to do this. First of all, it's e to the power, so it's itself, e to the tangent of 2z, right? Times the derivative of the exponent, which is tangent 2z. And you want to write some steps on this, so that's how the chain rule goes. So now if we move on, we're going to have e to the tangent of 2z. Okay, now when you do this, this is another chain rule. It's a chain rule again. So what is the derivative of this? It is the secant squared of 2z, but then you have to multiply again by the derivative of that inside part. So I'm using, really I've got a composition of three functions on this. So this is e to the tangent 2z times secant squared 2z, and then the derivative of 2z is what I should have wrote there, is times 2, like that. So when you clean this up, the best way to write this would be to bring the 2 in front and write this as 2e to the tangent 2z secant squared 2z. All right, so again, what I did is I did itself times derivative of exponent, but when I did that derivative of the exponent, I had to use another chain rule. Does that make any sense? That's like three functions, a composition of three functions. You could have a composition of 1,000,000 functions if you wanted to, okay? And theoretically, it'd all be done the same way, okay? Okay, so let me let you guys work just a little bit on this, and this would be pretty decent to see how well you do on these. These are, and really the rules you got to know on these are, you need to know what the derivative of the exponential is. You got to know what the derivative of the sine x is, and the other thing it looks like I got there is the derivative of the cotangent. So those are the things that you got to know, okay? And just do the second method and just see how you, if you can reason these out. Okay, let me go ahead and run through it. We're about out of time here, so let's go ahead and run through these. Okay, now the way I would look at this, first of all, you have a constant times a function. So you can just write down the constant. Don't use a product rule on this. I see the product rule works, but it's unnecessary. If you have a constant times a function, just write it down. Okay, so the key is, how do we do this derivative? If you do the derivative of an exponential, what is it? It's itself, right? So just write down itself. Now the chain rule says do what? Multiply by the derivative of that function. Okay, that's how you set that thing up. Okay, so now the answer to this problem is going to be 2e to the sine x times what? Cosine x. There's your answer. Okay, that's chain rule. So when you're doing an exponential, just think of it as itself times the derivative of the exponent. Okay, that will help you to kind of process that right. Okay, all right, now with this next one, we have f prime of t. So the cotangent's derivative is negative cosecant. Now this has a function inside, so you start by saying negative cosecant squared of 10t to the second, and then what do? You multiply by the derivative of that inside part of what that angle is. Okay, that's how you handle a derivative of a trig function using this rule then. Okay, so now what you would have is negative cosecant squared of 10t to the second. Okay, and then this derivative right here would be what? 20t, like that. That's your derivative. The best way probably to write this, it's always good to write stuff in front of trig functions, just so that you're not confused about that 20t is not a part of that cosecant. So the best way to write this is negative 20t cosecant squared 10t to the second, like that. That's your derivative. Problem done. Okay, what do you think? Not bad? Okay, it's all a matter of how you look at these things. Now this next one, we don't need to write this as sine squared theta. This, you can kind of think of this problem this way. It's a power rule problem. If you have the derivative of something squared, it's just 2x, right? This is something to a power. It's a power rule. So when you do f prime of x, you're going to bring the 2 down, and you're going to leave the sine x alone. You don't do a thing with it. Then what do? Multiply by the derivative of what's inside. Like that. Okay, so what you end up with is 2 sine x, and then the derivative of the sine is the cosine x. And that's okay. There is an identity. Does anybody know what that identity is? 2 sine x cosine x is sine of 2x. You can go that far if you want to. You don't have to, but you can. Okay? All right, so that's kind of the idea. I brought this little Russian doll thing in because when I think of the